Hello, everybody. I'm Jake from the Wild Labs team, and I'll be your host for this month's Variety Hour. We have some great speakers lined up for you today, including three speed talks from Baisakhi, Eduardo, Sofia, and an intermission and a Wild Labs quiz, which will run by Vanessa on Patagonia. And then finally, our long talk from Jesse. We'll start things off with Baisakhi, who will be talking to us today about how satellites and AI are helping to diagnose mangrove health. So, Baisakhi, the floor is yours. Please take it away and share your screen when you're ready.
Hi everyone, I am Vaishakhi, and this is my welcome to my love letter to muddy mosquito-filled spectacular forest. Today we are talking about mangroves. They are not just trees. We are talking about how satellite, drones, and a little bit of AI helping us to see their hidden struggles. Because let's be honest, uh, wading through crocodile habitats to count leaves is not everyone's dream job. So let's look at them from the evolving state. So mangroves, the blue carbon guardians. So first thing first, what is even a mangrove? They are the salt-tolerant trees which grows in tropical areas. Mostly, globally, we have around 147,000 square kilometer of them, and India holds about 3% of Southeast Asia's shares. But size is not everything. It's what they do matters, and they do a lot. And Here is the values. Mangrove stores 3 to 5 times more carbon than tropical rainforest, and they're worth a staggering $32 billion annually in fisheries, storm protection, and water filtration. And they also have various kind of other provisional services. Other if we look at them through sustainability, so they provide a lot of provisioning services, other services. But here is the bad news. We already lost 35% since 1980s, and that is like one third of their total during my parents' lifetime. So here the loss of health doesn't mean the loss of means loss of all these services. So which brings us to the $1 million question: how do we monitor health across this vast and inaccessible areas? So here is the hard way: the traditional field-based health assessment, where we do through quadra sleeve sample, mud core. And I have massive respect for field biologists. They are the real heroes. But this approach is time consuming and is point based. We can only cover a few parts of the total mangrove. But this app, and it simply doesn't scale. We have to extrapolate the data throughout the mangrove. So you can simply sample every hectares of 10,000 acres of forest. So we need a bird's eye view. So here come before jump into the tech. What is even health? It is not just green means good. It is a multidimensional. We look at structure, how tall it is, and how dense it is, and physiologically, is it photosynthetically doing well, and biophysically stuff like leaf area index and disturbances, has it cyclone or paste heat it. So remote sensing let us measure all four simultaneously, and that's the magic here. So let's comes to our integration, where we combine all these satellites, drone, and field data to enhance it, and we take ground data for training and pair it with drones for ultra resolution, and top it off with satellites for bigger picture. So when you fuse these three layers, you get a synoptic health map, a complete color coded report card for an entire forest in one image. And this is where the conservation meets data science. So here comes our workhorses, Lancet and Sentinel. And Lancet is like old and reliable because it has a 50-year of history and 16-day revisit time with a 30-meter of resolution. And Sentinel is new. It just launched in 2015. and it has a 10-meter resolution and 5-day revisit time. So, plus it has red edge bands specifically designed to detect the plant stress. Together, they are Batman and Robin of the mangrove monitoring. So, here comes the game changer, Google Earth Engine. So, earlier, what we have to do, like we have to download terabytes of data, and it uh, your laptop would cry, and you have to wait for few days to process those datas. Now I can write only 10 lines of codes and run it and process the decades of imagery in under a minute. So petabyte of data, zero download, and lightning fast analysis. And it democratized uh, satellite data for everyone, and even for grad student like me. So here comes the satellites are great, but they miss the fine details. That's where drone comes in. They do centimeter scale resolution, and we can build a 3D canopy model using structure for motion, especially turning the thousands of photos into 3D digital tree. And they also validate our satellite data. Think of drones as the ground truth team without the leeches and the mud and the crocodiles. Absolute lifesaver. And these are some paper which shows the use of drone use in this mangrove field. And here comes few case studies. It is in Australia. Its survey was dieback disease in mangrove, and how much it affects the total area. We can simply see through the map. We don't have to put so much of through data and tables. We can simply visually observe through it through the map. And next case study is from Mumbai, where I study now. So it is a case of defoliator outbreak, which is a pest, Hiblia puria. So it impact in this paper they cited like a 67.9% mangrove were defoliated, and what they did, this helped local authorities to pinpoint which creek zones were hit hardest, and so they could plan a restoration effort smartly. So from this picture itself, we can see that how much area these red points are highly infected and yellow are less infected. So from here itself, we can manage them through policy regulations. And here comes the future where we can integrate model like SATME, which have pre-trained on global satellite data. This means we don't need a tons of local field data to train models. And digital twin, it is like imagine a 3D stimulator where we ask what happens if sea level rise by 1 meter, and get an instant visual, and ultimately unified health index, a single global score for every mangrove forest on the earth. That's a dream, because it is still for global, there is no single unified health index for mangroves. So, but in this study, there are few challenges like cover, spectral saturation through high biomass canopies, persistent cloud cover in tropics, and tidal fluctuation mask the health signals. And sometimes we cannot reach the particular ground and to verify the exact data where we are collecting, where we are working through satellites. So this ground data is lacking. So here comes a takeaway message to wrap it off. Mangrove are the places where land meets the sea. So they holds they are protecting us from cyclones and different disasters, natural calamities. So with satellite and AI and a little bit of cloud computing, we have the tools to listen to their silent scream. And thank you so much for having me. Mangroves can speak, but their data can, and we need more brilliant mind to decode it. And reach out to me at email on your screen, and find me on through this wildlife website, and I would like to collaborate because I am from fisheries background and I don't have that much knowledge about the coding and all. So we can collaborate through coding because I am a biologist, I am not a coder. So we can collaborate. Thank you.
Thank you so much. That was a great talk. We don't have any questions in the chat, but if there are any, please add them to the chat, and maybe you could answer them directly into the chat as we move on. There was also
Yeah,
a
sure.
request if you have any of the paper links, it would be great to share those in the chat too.
Okay, okay,
But thank
okay.
you so much. That was great. Thank you. Next up, we have Eduardo, who is going to speak to us about ChatMPA, which is bringing AI-powered decision support to marine protected areas in Mexico. Eduardo, please take it away.
Hi everyone, thank you for having me. I'm Eduardo León, and I lead data science at the Center for Marine Biodiversity and Conservation in La Paz, Mexico. And today I want to show you about ChatMPA, a way to turn conservation data into decisions without losing the science along the way. So we start with a simple question. Is my MPA functioning? My marine protected area functioning? This is the question that drives everything. So a marine protected area exists to protect something, and as many of us may know, most of them are considered paper parks, which are affected in paper but not in reality. So a manager stands on the coastline and asks a simple question. Is it actually working here? And you may think we could answer that fast, but actually we can't. Getting this answer may take weeks. The data lives in scattered files and formats, and sometimes the answer is unreliable, and sometimes it's just impossible to produce in uh, time to matter, right? So the people asking or making decisions rarely have the analysis ready when they need it. And this is not a data problem. We have the data, we have tons of data. The problem is the distance between the raw data and the decisions. And us, scientists, I'm a marine biologist myself, is to bridge the gap between raw data to conservation intelligence. And the way we do this is usually we start by connecting different data sources, the ones we gather in field trips, the ones we gather from satellites, then analyze it, interpret it, and deliver it, socializing to the people who need the most, like communities, decision makers, or park rangers. So our goal is conservation intelligence, and two pieces make this work. The first one is the model context protocols, or the MCPs. These MCPs lets an AI connect directly to live and verified data sources, not a copy someone exported last year and forgot about it and is living somewhere forgotten in their computer. Uh, we can picture the MCPs as the new USB adapters for data. So we have one standard plug, and suddenly every data set speaks the same language. We can connect it to different AIs, LLMs, and we can ask questions directly to the data sources. So for ChatMPA, the idea is that we gather every different data source into a single ecosystem hub, and not only the global datasets from Skylight, Marine Protection Atlas, Ranger, Global Fishing Watch, but also the data we gather as scientists in our day-to-day jobs, from vision, from cameras, audio, satellites, or remote sensing. And the second piece are the skills. Skills are standardized ecological or scientific analysis workflows. So each one answers to a specific conservation question the right way every time. We think of this as having a scientist 24/7 validating and conducting analysis. So the method doesn't drift depending on who asks or when. So, for instance, if we feed our dataset to some AI and ask it to deliver some plots about fish biomass trends or and gather some conclusions, today we might get this. But if we come back later, the same day, the same week, or the next month, we get similar results, but not quite the same. So a skill locks down the analysis. So the same question, same method, same result every time. And this is how they fit together. First, the MCP moves the data. It opens the dataset to plain language questions. So for instance, in our prototype, we have integrated 4 datasets, one from ourselves, which is the ecological monitoring of rocky reefs in the Gulf of California. We have gathered more than 26 years of data. The second one is the Conapesca, or the fishery records for Mexico, and some environmental covariables such as sea surface temperature and chlorophyll from NASA. And the skills then decide the science. We have now the datasets open and we can use that. So we load the skills and each one fixes the method, the parameters, the random seeds, and all of these skills are human verified. So they are peer reviewed. So this is how we can call the data sets and then we can analyze it, and we don't have to be experts. For instance, I don't know how to conduct socioeconomic studies, but if some expert already validated the skill, I can use it. So we're thinking of ChatMPA as this ladder system built from 5 capabilities from the ground up. The first one is the scientific memory, or the MCPs. We start by making all these datasets open, and then we build the ecosystem intelligence, which is our day-to-day task as scientists. We're conducting workflows, ecological analysis. Then we move to decision intelligence, where we start working with other scientific experts in the group, from climate change experts to socioeconomic analysis. And then we can reduce these workflows and these pipelines to trustworthy scientific AI, which are the skills. Then the last part, the most difficult part, is adaptive governance. We then encapsulate all of this science into a single platform, which every user can use, which can be a dashboard. So we have a living prototype, the ChatMPA dashboard, in close collaboration with the National Commission of Natural Protected Areas in Mexico. We're working with 2 marine protected areas, which are Revillagigedo and Cabo Pulmo. And the way we do this is we give them a user, a password, they log in, and they can start chatting with the AI chatbot we have incorporated, asking questions about all the data we have gathered for those specific MPAs. And they can also do some other cool stuff, such as plot trends, see their current status of different indicators about their marine protected area, write automatic reports or management plans. And finally, none of this is a solo effort. It's built on open standards and open science with partners across conservation, research, and technology. So we're standing on a lot of shoulders and we're building this in the open so others can too. So that's ChatMPA, from science to decisions without the science getting lost in between. So if you work with marine protected areas or if you're building something similar in your own domains, I'd love to talk to you. Thank you.
Thanks very much. That was a great talk. I think maybe if people again just ask questions in the chat for Eduardo and you can answer them directly. But thank you very much. That was a great talk. Okay, next we have our final speed talk, which is from Sophia, who will be talking to us about CanAvian, furthering biodiversity research through a national data space. So Sophia, if you're ready, please go ahead.
As Jake mentioned, my name is Sophia. I'm the CanAvian coordinator, and I'm going to be talking about how we as CanAvian are furthering biodiversity research through a national data space. So birds are among the best studied animals in the world. However, bird data is collected in different ways by many different people, and it is stored in different places. And this can make it difficult to find and access the data you need. That's why we're working towards a national data space for bird data in Canada. The CanAvian community is built around bird data, where our community members collect, interpret, and manage and share data to further the understanding and the conservation of birds. We're working towards a national data space where we have independently developed biodiversity data systems, which are working together on the basis of interoperability, which depends on shared policy, trust, and technical exchange. So CanAvian was formed in 2019 by Birds Canada, the Alberta Biodiversity Monitoring Institute, Biodiversity Pathways, and Environment and Climate Change Canada. These groups were all creating and curating large avian datasets and research software tools independently and came together as CanAvian to improve access and interoperability of these datasets. Currently, these partners manage several biodiversity data resources, which are used to store and interpret biodiversity data. These resources have both national and international reach. CanAvian itself does not store any data. Instead, it connects platforms which already do. Our focus is on collaboration and interoperability. So today, CanAvian is a formalized partnership which includes some of the largest biodiversity data platforms in Canada. Our focus is avian data in Canada. However, our platforms have data from many species across many different countries. Together, these different data platforms have billions of records and engage over 850 organizations with 35,000 registered users worldwide. Each platform retains its own mandate, community, infrastructure, and data holder relationships, but CanAvian aligns the governance, the standards, policies, and data exchange pathways across these systems. We prioritize collaboration, not consolidation. We are now a part of a pilot program by the Digital Research Alliance of Canada, or DRAC, which is working to establish a national data space. Over the next 2 years, with DRAC support, we are formalizing shared data policy, focusing on FAIR data, which is findable, accessible, interoperable, and reusable, with a focus on CARE principles, which are the collective benefit, authority to control, responsibility, and ethics. And we're very excited to be working towards shared standards and interoperability, a shared governance structure, and building up the CanAvian community. Our aim is to have trusted and connected bird data that supports conservation and research decisions. So why does this matter? CanAvian aims to connect data with users who support bird research and conservation in Canada and across the world. High-quality information organized in a user-friendly way with set standards and tools makes it easier for researchers and conservation groups, communities, and decision-makers to access information and use it to better understand and conserve birds. This comprehensive, high-quality, harmonized data is critical for researchers which are applying new analytical techniques that rely on large, harmonized data sets. That research is essential both for understanding and conserving birds and for fulfilling international commitments like the Kunming-Montreal Global Biodiversity Framework. By aligning standards and reducing duplicated effort, we keep bird data accessible, well-managed, and useful for the people who rely on it. Bird data is a natural place to start for this pilot, but what we learn can be used to help improve how all biodiversity data is collected, managed, and shared. So thank you so much for your time. We've made a forum post, which I'll link in the chat in a second here, which includes some of the following questions. But if you have any questions, I'd love to hear them, and I'd love to hear how you can see yourself in the CanAvian community. If you see yourself in the CanAvian community, what does that look like for you? And if not, how do you think data community in your part of the world could interact with CanAvian data space? Thank you.
Thank you very much. That was a great talk. We have 1 minute, and I have a question from one of my team actually, which was, if another country wanted to build a CanAvian-like initiative, what would be your first piece of advice?
I would say start with the projects which already exist. Start by looking at what are the data resources that are currently there and who's working to share data, and start with more of a ground-up approach. That's the approach that we're taking, and it's following similar to things like CanBon and other bond processes which work on biodiversity data, but we're looking at what's already there and how can we support those groups and work towards more interoperability and collaboration to make that data go farther and mean more.
Great, thank you. I'm seeing more questions in the chat, but we need to move on. So feel free to answer those questions in the chat, and please do ask some more. Thank you very much.
Thank you.
Okay, right. So now we are moving on to our ad break. So that wraps up today's speed talks. So yes, time for the Wild Labs ad break. First up is an announcement that Wild Labs is available in French. So Adrian, could you help elaborate?
Yeah, I hesitated to do this in French, but probably only a couple of people, maybe the Canadian people would have understood. But it's my great pleasure to introduce Wild Labs translation in French after the addition of Spanish a couple of months ago. You can now browse Wild Labs in French. You can share content in French, automatically translate some documents that are or comments that have been shared in another one language that is not French. So yeah, that's something we are very proud of, and we invite you to visit WILDLABS.NET and choose your language of preference now between French, English, and Spanish. And the other announcement I'm super happy and proud to share with you today is that the awardees 2026 cohort is now known. So we, after 4 months or 6 months even of deliberation, shortlisting after the expression of interest, judging panel, experts intervention, chose 16 projects, 11 projects from the 10K category and 5 projects from the 50K category to be awarded this year. So you are welcome to visit the page that will be shared in the chat to know more about this project and to discuss directly with the project leaders that will be happy to answer your questions.
Great, thank you very much, Adrian. So next, we're going to be moving on to the Wild Labs quiz, which is about Patagonia, and it's hosted by Vanessa. Vanessa, over to you.
Thank you, Jay. Hi, everyone. I'm Vanessa from the WILDLABS team. I'm now currently in Patagonia in Argentina, so I decided to do this quiz. I hope you enjoy it to learn a little bit about this amazing place. So first question, Patagonia is approximately the same size as which of these regions? Alaska, Greenland, Spain, South Africa. You can drop your answers in the chat. Spain, A. A lot of A, couple of Spain, Greenland. Well, it's actually much higher than Spain is. A lot of you made it right. Next, Jake, it's Alaska. It covers about 1 million kilometers square, which is roughly the size of Alaska. But it's home to fewer than 3 million people, which makes this place one of the least densely populated regions on Earth. So next question. Which Patagonian town is home to the world's largest known breeding colony of parrots? Puerto Madryn, El Cóndor, Ushuaia, o El Calafate? A or D? C, 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 C. Okay, a lot of Ushuaia. Ushuaia, that's probably one of the most known cities in Patagonia, but the answer is actually El Cóndor. No one get it. El Cóndor is a small town in Rio Negro, and there is a 12-kilometer sandstone cliff which hosts the world's largest known breeding colony of burrowing parrots with tens of thousands of nesting burrows, and it's super crowded. It's crazy if you are there. Next question. Which predator in Patagonia is famous for a unique hunting technique? Puma, orca, Andean fox, or basking shark? Stephen said orca, orcas, basking shark, orcas, a lot of orcas. Well, maybe basking shark also have a unique technique, but the answer is, Adrian says puma for penguins recently and orcas for seals. Yeah, orcas. So they have this amazing behavior where some of the individuals beat themselves to catch sea lion pups, and they learned this behavior by watching experienced adults. So this is a great example of cultural transmission in marine mammals. Next question. How far can a red knot fly without stopping during its migration between Canada and Patagonia? 2,000 kilometers, 5,000 kilometers, 8,000 or 12,000 kilometers. I'm seeing B, D, C, C, and yeah, the correct answer is C, 8,000 kilometers. And without stopping, which is crazy, I think. And yeah, and they do this stopover during this transit. Last question, I think. How old can a Patagonian alerce become? About 500 years, about 1,000 years, more than 3,500 years, or more than 10,000 years? Oh, yeah.
I was just saying, there might be a clue, but it is camouflage.
There might be.
So don't...
Maybe. Okay, I'm sorry about that. Yeah.
Well, it might be different.
You are correct. Well, maybe maybe someone can guess exactly. Well, is this more than 3,500 years? And there is one record of this famous Gran Abuelo in Chile, which was estimated to have more than 5,000 years old, which is crazy. Okay, thank you so much. I hope you learned something and enjoyed this quiz. I'm sorry about that clue.
Thank you very much. That was a great quiz. I learned more about Patagonia, and I hope you enjoy the rest of your trip there. Absolutely. Great. Okay. So that was the Wild Labs quiz. Thank you, Vanessa. So now we're on to our long talk for today. We're a bit early, so you have more time for questions maybe at the end. So for our long talk, Jesse will be talking us through Open Toolkit for Animal-Borne Acoustic Monitoring. So Jesse, if the floor is yours, if you're ready.
My name is Jesse Turner, and I'm a PhD student at Colorado State University. And I'm going to be talking about a collaboration between Colorado State and Vanderbilt, which is an open toolkit for animal-borne acoustic monitoring. And this is one of the awards that was for the Wild Labs Awards 2026. First off, I'd like to define the field a bit. When I talk about animal-borne acoustic monitoring, I'm going to be referring to it as audio logging, which is a term that's used by many practitioners, as well as one that encapsulates the constituent parts of the field, namely passive acoustic monitoring, which you all are probably familiar with, but just recording the soundscape around us, and biologging, which is when we attach sensors to individual animals. And so when we combine these two, we get audio logging, which effectively takes the scale of acoustic monitoring down to the resolution of an individual animal. And it lends itself pretty obviously to bioacoustic research because all vocalizations made by the focal individual are recorded by an audio logger. But there's also a wide range of other phenomena that can be detected, such as physiological sounds like respiration, anthropogenic noise impacts or impacts from other environmental noise. We can also record movement and feeding-related sounds and community interactions that are acoustically detectable. And I think what audio logging is enabling us to do is kind of a pattern that we've seen over the past decade or two with passive acoustic monitoring more in general. And that's a transition from being mainly detection-based to actually being able to resolve more information, such as behavioral information from vocalizations. So traditional uses of PAM largely have been, at least historically, extracting a vocalization from background noise and using that presence of the vocalization to determine presence, absence of a species, perhaps abundance or distributions in space or time. But as machine learning and computation has increased, we've been able to extract additional information from vocalizations because they are honest signals that encode a lot of biologically relevant information. But we need context in order to make that association. And with wild animals, that is often very difficult to get that context with traditional systems. But audio loggers can provide that context. So we can look at behavioral bioacoustics, or when specific vocal behaviors are correlated or can be used as a proxy for specific behaviors. We can also look at correlations between vocal behavior and movement. It's very common for audio loggers to be as part of a multimodal system with either GPS, which allows us to look at large-scale movement, or accelerometers, enabling us to look at fine-scale movements. And also we can assign vocalizations to a particular individual, which can be very difficult with traditional acoustic monitoring systems. We can also look at responses to environmental noise. So everything that the audio logger is recording, the individual animal is also hearing. So if there's any response to an environmental noise, whether it be from humans, other animals, or the general environment, we can research that as well. So the real gap right now is that there's no off-the-shelf or open source audio logger systems that exist today. And so this leaves us with two different possibilities. We can either modify existing off-the-shelf systems, which this team to the left has done by attaching a voice recorder onto a collar deployed on a Panda. But these are not going to be optimized for the task. They might not be as durable as they need to be. They're probably not as power efficient as they could be. And so they're not perfect for the situation in which they're being deployed. And on the other end of the spectrum, we have fully custom systems. And so we have a team there on the right that deployed a custom audio logger on an African lion. And these are obviously very optimized for the task, but they require pretty significant resources and expertise in order to develop a system like that. And that's something that most teams that are interested in this sort of research don't have the capabilities. So our solution to this is an open source audio logger system, an end-to-end toolkit that's based around the Apollo 4 microcontroller. You can see a picture of the board on the bottom right there, which boasts a low power consumption, configurable sample rate between 8 and 48 kilohertz, and an onboard accelerometer that enables us to detect those fine scale movements. We've incorporated a variety of features to make it as easy to use as possible, namely a removable SD card that is both used for data storage as well as configuring the acoustic settings. It writes uncompressed WAV files, meaning that no proprietary software is needed for downloading and listening and analyzing the acoustic data. And a simple magnet can be used for activation and deactivation. A key feature of our system has been a modular approach. So we've realized that there's a wide range of different species that this could be applicable for, with different sizes, different attachment mechanisms. And so having a modular approach enables us to be flexible depending on the application. So we have CAD designs for 3D printed housings that can be modified depending on the size. Additionally, battery packs can be increased or decreased in size depending on the requirements for lifespan and weight. The board can be used with either analog or digital microphones, and we've been experimenting with a variety of different drop-off mechanisms because the GPS collars themselves generally last a lot longer than the audio loggers do. And so a drop-off mechanism enables us to collect those data before the collar is actually removed. And so I have pictured below just a couple of examples, a mule deer deployment on the left in Colorado, which had a 3D printed housing, an analog microphone, and no drop-off, so it was just permanently attached. And then on the right there is a deployment on an elephant, which we used an aluminum housing, a digital microphone, and integrated it with a Telonics drop-off mechanism. So I'd like to touch on the data and the adaptive data collection aspect of the board. But first, I want to briefly mention why we wouldn't just continuously record audio. It's kind of obvious, but if we're continuously recording, the more data we're collecting, we're going to run out of power and storage faster. So we're going to decrease the lifespan with continuous recording. But more importantly, we're gathering a lot of irrelevant data. So it's pretty rare that an acoustic monitoring project will actually use all of the acoustic data. Generally, we use a very, very small subset of the data. It's just that the trick is with embedded systems, it can be tricky not to discard the relevant data that we actually want to retain. So to that end, we have implemented and are also developing some different strategies in order to not just be continuous recording, which is a possibility. So on the left there are some data reduction techniques that are more standard and you might be familiar with, such as amplitude thresholding to discard periods of relative silence, as well as frequency band triggering to only record time periods when there's some activity in the frequency band of interest. and time-based filtering, like duty cycling and scheduled recordings. And all of those have already been implemented on the device. And on the right side, we have a couple of more intelligent data collection strategies that are in development. More specifically, a variational autoencoder, which effectively translates a sound into a numerical representation where similar sounds will have more similar representations. And then we can have a decision tree on whether to record or discard those data, depending on, for instance, cluster density, which would be indicative of how rare or common that sound was. So we could only record more rare sounds and discard common sounds that would probably be background noise. We also have the capabilities of more computationally intensive classifiers to run on device, but generally these use more power than continuous recording does. So they're useful in reducing the total amount of data, but not in reducing the actual power consumption. But still, for our larger systems with bigger battery packs, we're effectively storage constrained for those systems. And so this technique could still be useful in extending lifespan. I'd like to highlight a few case studies of focal species that we've been deploying on. So this is the African savanna elephant, where we are conducting a study on vocal communication. Specifically, we are monitoring call rates and looking at the correlation between vocal and movement behavior. We've deployed a total of 19 different systems, and out of the systems that we've recovered, we have a max recording duration of 36 days. However, those systems were on a much less power efficient firmware. So the ones that we're currently recovering, we anticipate about 120 days or 4 months of continuous audio. Another focal species has been bighorn sheep. And the purpose of this project is actually disease monitoring. So we are acoustically detecting coughs as an indication of respiratory disease, which is a big problem in bighorn sheep in the Mountain West, where pneumonia is a pretty significant cause of mortality and also can cause acoustically detectable coughing symptoms. We've deployed 5 total systems on bighorn sheep and have a maximum recording duration of 45 days. And the last case study I wanted to highlight is a collaboration with the Scandinavian Brown Bear Research Project, where we are deploying a few systems on brown bear. And that team is actually interested in acoustically characterizing predation events. And we've deployed 5 systems on brown bears, and the recovery is currently in progress, but we anticipate at least 40 days of continuous audio coming from that system. So although all of those projects have so far gone smoothly, they've required a significant amount of resources and time from our team, from customizing the housings to attachment mechanisms, also configuring the acoustic settings and testing the fully end-to-end systems. And this is just not feasible on a larger scale or in the long term. So we're in the process of developing 3 different template sizes for different species, where we have a small, a medium, and a large, with the goals for design specifications listed here in terms of weight, recording lifespan, housing material, and build cost. And I'd like to point out that the recording lifespan there, that's based on continuous recording. So if we utilize any of the data reduction strategies that I previously mentioned, then we can greatly extend the lifespan of those systems. Another front that we're pushing forward on is the software development. So we are working on refining the firmware in hopes for more power efficiency gains, as well as direct integration of the audio logger board with GPS collar systems from Savanna Tracking. We're also creating edge models, both supervised models for on-device classification, as well as unsupervised models like the variational autoencoder, which can be useful in more intelligently deciding which data to store versus discard, simply based on the soundscape in which is deployed. And lastly, we'll also be working on the configuration interface. So pictured to the right there is a screenshot of the graphical dashboard that will be continuously updated and made more user-friendly as the project moves on. And for our team and for Wild Labs, open source is really a key focus. So all of our software and firmware is on GitHub and will continue to be updated as we move through the project. We'll also be developing assembly guides and manuals that will be publicly available for how to use the system, and CAD designs for the housings that can be either used directly or easily modified if the size or the design is slightly different depending on the application. And any AI models that we develop as a part of this project will be released to Hugging Face. So we're looking for collaborators who are interested in pilot deployments. So if anybody is hearing this and thinks it could be applicable for their system, please reach out. And picture to the right there is just our GitHub account with all of our software and firmware. So that's all I have. Thank you guys so much for your time. On the right there is a QR code that you can scan, which will take you to our website where you can get some more details about the system. My email is also listed there if you'd like to reach out. We're specifically interested in hearing if there's any specific development that would make this system more usable for your application, or if your team would be interested in testing a pilot deployment. We'd love to hear from you and potentially start a collaboration. So thank you guys very much.
Thank you very much. Another great talk. We do have time for questions. I don't see any questions in the chat right now, but I have some from my team. Which species or taxonomic group do you think stands to benefit the most from this technology over the next few years?
Good question. I think, we have noticed, like, in terms of the attachment mechanism, GPS collars, lends itself really nicely to this work. And so I think GPS collars are really going to be the attachment mechanism that we're going to be focusing on. And to date, we've largely focused on, at least internally, on ungulates. So I think that's going to be the species that we're going to be mostly focusing on. However, we've also had other teams, like I mentioned, that brown bear project that is, also using it for acoustically characterizing predation. And so it definitely works for carnivores and other species as well. But I think ungulates are probably going to be our focal taxonomic group.
Great, thank you. I did see a question from Nathan. Do you have any plans to integrate with Iridium or anything similar?
Yeah, so I mentioned briefly that we're directly integrating the audio logger board with GPS system, and so our GPS collar system, specifically one from Savannah Tracking. And so the end goal is to not have the audio logger itself actually directly connect with Iridium, but instead integrate the audio logger board so it directly actually connects with the satellite system that's already being used by most GPS collars. So instead of reinventing the wheel, we're hoping to be able to more directly integrate with systems that already have that capability. But what that would enable us to do is any sort of real-time alerts. And so there's a couple of instances that we're interested in, like gunshot detection for poaching, or it doesn't have to necessarily be gunshot, but just human sounds where there shouldn't be human sounds. And then also for instance, the bighorn sheep system, cough detection. If we had a system where it could detect a certain threshold of a number of coughs per day, then we could, in theory, have an alert that says, oh, there's a potential outbreak that's about to happen based on acoustically detectable symptoms.
Great, thank you. Another question from my team. What would success look like for this project as an open source community rather than just a research project? How do you hope other researchers will contribute?
Yeah, so it's a great question. I think success for us looks like the ability of teams to be much more autonomous in their use of this system. All of the deployments that we've done to date have been extremely labor intensive from our team, which has been by design because we want to be involved. But as we scale up and deploy on more systems, that's not becoming feasible. So what we're hoping is that we can kind of take our foot off the gas and not be as directly involved. We'll obviously still be available and in contact for any issues or concerns. But I think for us, success looks like people being able to autonomously deploy these systems on their own without a lot of input from our team.
We have some time before the end of the call if there are any other questions. Jesse, have you encountered concerns about filtering out data on the edge?
Absolutely. Lots of concerns, yes. That's why the more standard data reduction techniques that I mentioned, the ones, amplitude filtering, frequency-based triggers, those are not like intelligent data collection methods. And that's why we're, still developing the intelligent data collection methods, because it's not only, a matter of filtering out data at the edge, but it's also because these are animal-borne systems, they're not the acoustic data don't look like, most other acoustics projects, right? Because we have, sounds from rubbing on the system or from breathing, and so it's hard. It's, like there's a lot less silence than you might think, because there's all of those interferences. And so we've definitely had a lot of issues with, filtering out data. But we're confident that, that some of these, like the variational autoencoder, for instance, can be still useful in particular systems. And I don't think it's going to be like, a reduction of like 95% of the data, but it could be a reduction of something more like 50% of the data, which would still, could potentially double the length of the deployment. So still useful, but yes, we've definitely encountered a lot of issues with, filtering out the relevant data that we want to keep.
Another question from Frank. Frank, do you want to ask this one on the mic?
Yeah, I guess I was just curious about, because obviously every sort of area and environment for these species, I imagine can encounter, environmental challenges as far as like device longevity and, protection for the device just from working in like a rainforest habitat. So I was just curious as far as when you design the, protections and things for that device, if, you have to consider specifically factors like cold or humidity or even behaviors like from the, focal species itself that could damage the device.
Yeah, absolutely. So we've deployed a couple of systems on caribou in winter up outside Fairbanks, and so that was probably the coldest side of things. It was obviously very, very cold up there, and we did encounter some issues with the analog filter or the analog microphone that we were using at the time, and it was basically failing because of the temperature, and so. Our batteries, I did a lot of research to make sure that the actual cells we were using would be fine. And obviously we, decreased the lifespan by quite a bit in those temperatures, but we were able to record data. But yeah, we noticed that the analog filter in cold temperatures, or the analog microphone, excuse me, in cold temperatures was problematic. But I think, the goal right now, all of our systems have been potted. So we're not, we're less concerned about humidity, water, temperature because of the temperature is obviously still getting there, but because we're potting all of our systems, we're not as worried about, water intrusion or capturing, humidity in the air when we close up the system. And I'm definitely thinking about different strategies for that, because when you introduce potting, that makes open source systems a lot more difficult to manufacture. So, and also it also increases weight. But we found that especially for some of the more difficult systems, like for African elephants, for instance, that is a very, very tough system. But we so far haven't had any actual mechanical failures of the acoustic board or the acoustic system itself, because we've been, potting and using aluminum housings. But I think, yeah, in the future, if we are able to, design a system without potting, I think we'd still want like some sort of desiccant inside the housing because yeah, it's always, especially in rainforests. You always, you get the water or you get the air in the housing, and then the temperature changes, and then yeah, all the rest everybody knows about. So, but yeah, I think potting compound has really been a lifesaver for us on that front.
Well, thanks again. That was a brilliant talk. Thanks very much. Thank you so much again for everyone, all of our speakers. We really appreciate you taking the time to speak to us today. And thanks for everyone for joining as well. We hope to see you in the next month's Variety Hour. Thanks for coming.